comparison test. What this says basically is if we have some series, and we'll denote this as AN, and we're not sure if it converges or diverges, but we know that there is another series, and we know some stuff about this one already. For instance, let's give an example that we know this thing converges. Okay, and we also know that for n greater than some value that we'll represent as capital N in this series, after it gets big enough, we can always say that the value of Cn is greater than An. Now here's where our comparison comes in. If we know this series converges and the nth member of that series is bigger than this nth member of this other series, by definition, by this rule, by theorem 10, this series must converge also. It's a little bit like our one-way sandwich rule, that if this converges, this must, because this is always on top of this. And in just exactly the same way, if we know this series diverges, and we know, let's get rid of this, that Cn for n greater than some value n is always less than An. Well, now if this thing diverges and it's smaller than the nth term of this series, then this must diverge. Pretty simple stuff, really. Well, if it's so simple, let's try an example. Let's take the example of a series that looks like this is example 1 in the book. Now, as is often the case, we have this series. We have no idea if this converges or diverges. And you just look at it and it might be a little confusing. And so if there is some series Cn that we know its fate, maybe we could use the comparison idea to get an answer. Does this converge or diverge? So what would we use? Now it turns out that if we apply a little trick of multiplying the numerator and denominator by 1/5, this series turns into something that looks like this. Now that looks a little bit more familiar. It looks a bit like the harmonic series, like this. We know this harmonic series diverges, and we also know that this term, this nth term, An, is always going to be greater, because the denominator is smaller, than the nth term of this series. Therefore, if this diverges, this must also diverge.